are going to be live on Facebook, and then I'll start the recording. Well, it looks like we are live right now on Facebook. Glad to have everybody on board. And we want to say welcome to everybody. And just to let everybody know, we are going to start recording this so that we can make sure we have this for use in the future. So we are connected to our cloud and we are recording. And it is 3:01 on July the 30th, 2020. Welcome everybody to the Fulshear-Katy Area Chamber of Commerce webinar. We have today with us from our, and thank you for our Government Affairs Committee, and we'll introduce Tommy in a moment. Again, I'm Don McCoy, President of the Fulshear-Katy Area Chamber of Commerce. And today we are doing something that is part of our mission statement. You know, we as a chamber always want to connect our community. That's what we do. We are catalysts for business growth, but we are also champions of the community. And part of what we want to do is keep everyone informed with the people that we deal with on all levels of government, from the county, state, federal level. And we like to bring wonderful people out here to tell you about what's going on in our world around the Fulshear-Katy area. And today we have a special guest, and we'll let Tommy introduce him. And just to let you guys know that your questions can be typed in the chat section if you're live right here on our Facebook page, on the webinar, and we'll get to those towards the end of the presentation. So with that, to start off, I'd like to introduce you to Mr. Tommy Kirkendall, who is the chairperson of our Government Affairs Committee. It has been since its inception. I can say great things. Our committee has been very active in keeping us here at the Chamber and the community at large informed as to all the things that you might need to know. So with that, Tommy, I'll let you introduce our guest today.
All right, thanks, Don, and I want to welcome everyone who's joining us today. Again, this is the Fulshear-Katy Area Chamber of Commerce Government Affairs Committee. We have a group of people that work really hard together, so I can't take all the credit. But what we want to do is bring programs to our members, but also to our local community that communicates information in a timely manner, and also to help educate the public. So let me just set the stage just a little bit for our discussion today on the Bessie Creek Watershed Study Update. If you remember, it's been nearly 3 years to the day that we experienced Hurricane Harvey in 2017, and we watched about 7,000 homes sustain damage. Fort Bend County has some great assets, but we also have some issues and natural terrain that we have to deal with, uniquely with drainage characteristics, including the Brazos River, the Barker Reservoir, numerous levee improvement districts, all combined with a high rate of growth and development. And last year, if you remember, in 2019, Tropical Storm Imelda pounded East Houston and Southeast Texas almost 2 years to the day of Hurricane Harvey, dumping over 40 inches of rain between the cities of Winnie and Beaumont, Texas. Last year in 2019, the Fort Bend County Judge and our County Commissioners Court called for a nearly $83 million drainage bond election referendum. And we're thankful that this initiative passed with nearly 70% of voter approval. So I think you can see how important drainage is to our region and our area. We're thankful today to have Chief Drainage District Engineer Mark Vogler to present and discuss the Bessie Creek Watershed study that's been conducted. And that flowed forth out of those recent flood events and also out of the flood mitigation bond approval. Now, Mark and I probably have known each other longer than both of us would like to admit, but he was born and raised here in Fort Bend County. And in my opinion, he has the most extensive knowledge of the history and the details about drainage within Fort Bend County. He graduated from Texas A&M in 1982, and he's been with the Fort Bend County Drainage District ever since that time. The Drainage District in Fort Bend County is responsible for maintaining over 600 miles of drainage channels and also reviews new development plans to ensure that they comply with the latest Fort Bend County Drainage Criteria Manual. Mark and his wife of 36 years live in rural western Fort Bend County. He has 4 daughters that have all graduated from college, But more importantly, he tells me that they've all gotten jobs and they're off of his payroll. So I know those of us who are parents can really appreciate that statement. So with that, I want to thank Mark and welcome him for his presentation today. Mark?
Stand by.
Mark.
I'm unmuting Mark. Okay, Mark, there you go. All right, Mark.
Can you hear me now?
Yes, we can. Mark, say hello to everybody.
Okay, thank you very much. I appreciate the opportunity to make this presentation. Let me forewarn you, I'm on my county office phone. My cell phone doesn't work inside this metal building, and so my office phone, when people call in, has a dinging noise. So if you hear that, I'll just pause shortly, let the call be answered by somebody else, and we'll go on with the presentation.
Okay.
With that, are you guys going to call the presentation up on your slide, or are you going to use my computer with the presentation?
Yes, sir. I'm going to share the screen here, and I have your presentation. And then, Mark, whenever you want me to change the slide, just let me know. Just say, please, next slide, if you don't mind. Okay.
Sounds good. Let's
right.
roll it.
So here we go, ladies and gentlemen. I'm going to share my screen right now with everybody. And here we go. And this is the slide right here. And I hope everybody can see this. All right. And there we go, Mark. So you can go ahead and you made your introduction. How about I go to the first slide, Mark? Would that be fine?
That'll be great. That'd be great.
All right. Here we are.
Okay. What this slide is showing is there's the location of the particular Bessie Creek, what I call Fulshear Creek, Brookshire Creek, and Orchard Creek watersheds within the county, the actual channels themselves. Also, a side note, the county is looking at a total of 41 major creeks and streams in the county and what those cost to upgrade those channels to handle an Atlas 14 rainfall, which is 16.5 inches of rain in 24 hours. Our previous criteria was based on a technical paper 40 that came out in 1960 from the National Weather Service, which said a 100-year rainfall for Fort Bend County at that time was 12.5 inches of rain. So all our previous criteria that we used on developments and reviewing and making sure that they weren't causing impacts were based on 12.5 inches of rain in 24 hours. We're in the process of upgrading that. We've got some interim criteria that we're using as developments are moving forward, but plan to get our criteria manual updated and put it into effect going forward as soon as this watershed study is completed. Next slide, please.
Okay.
This is just first couple of slides are just an overview of what's being used. Some of this is probably not making any sense to some of you folks. Then we're going to have a few slides to get really technical, and I'm sure Greg and John and Tommy are interested in it, but I think most of us are just thinking, yeah, get onto something I can understand better. But let me go with this slide. We have some draft results, and that's what I'm showing you here. These draft results have been changed since our last presentation. We did a presentation back in June with information we had at that time, but we had some changes that we wanted made we thought were critical, and so those are going to be reflected in this. With that being said, this is also not a final submittal, and it's subject to further changes. We are still working on our drainage criteria, and there may be a necessity for these engineers to go back and upgrade this report even further as our criteria gets upgraded and changed. The consultant doing this particular study is Freeze & Nichols, and they're using these HEC-RAS models and HEC-HMS models. And let's go on to the next slide. That's not really critical at this time. This shows you the watershed of Brookshire Creek, Bessie Creek, and Orchard Creek. And as you can see, Bessie Creek goes well up into Waller County. It goes all the way up to Monteville. That's about 15 miles as the crow flies north of the county line. And Brookshire Creek goes well up into Waller County also. So a tremendous amount of flow that comes through this drainage system is coming from Waller County. And we have to accept that water at whatever rate it comes down. As you get to the county line, the topography changes significantly on Brookshire Creek. It has a very steep slope coming into Fort Bend County. And once you get into Fort Bend County, for about the first 2 miles, we've got a very flat slope here. So a lot of water runs out of Waller County into Fort Bend County, not by anyone's fault. That's just the way the land is sloped. This is something that John and Greg and Tommy may be interested in, but this is basically just showing what each sub-area that Bessie's Creek and Brookshire Creek and Orchard Creek are broken into, what some of the characteristics of those are, what the area is, and for the respective storm rates, the 2, the 5, the 10, the 100-year, and the 500-year, how much water would be running off of that particular sub-area in a 100-year event. Next slide, please. This is just a representation of the portion of the Brookshire Creek, Bessie's Creek, and Orchard Creek watershed within Fort Bend County. If you notice the picture on the left-hand side, there are a couple of areas outlined in red. Those areas are actually not included in the Bessie's Creek watershed. I know the one to the south, the lower one, that one, had naturally flowed into Bessie's Creek for a long period of time. But Stanley Kacherka and Dan Gherkin, my previous bosses, had always been on Western Lakes to incorporate that into its own outfall system to the river. A significant portion of Western Lakes was developed, but when it got to its last few sections, and then the development of Fullbrook came in right around that Oxbow Lake, they were able to complete that and get an outfall channel. So that area drains to the Brazos River separate from Bessie's Creek or Fulshear Creek. The area on the right is basically breaking down the county or that particular watershed into sub-areas, and we'll have more information on the details of each sub-area as we get further into this. Next slide. This is the Atlas 14 rainfall, and again, as I mentioned earlier, we're using Atlas 14 in Fort Bend County, 100-year. So if you see 1 day, at the top chart, 1 day, 100 years, 16.5 inches in 24 hours. That's the 100-year rainfall we're using on these 3 watersheds. Warner County has a little bit different number. If you look at the lower chart for 1 day and then go over to the 100-year rainfall event, it comes out to be 15.4 inches in 24 hours. And so the engineers that were modeling these watersheds broke them up into counties with these different rainfall events occurring there. Next slide. This is one of those, again, Tommy, John, and Greg are probably liking it, but this is a methodology that we're using to determine the impacts of the ground, what type of soils are in there, how much water infiltrates in the ground, the slope of the ground, how much water runs off, those type of things. And so these are criteria that engineers may be interested in, but for the general group, I'd say that's enough conversation on this one.
Next slide. Next slide.
Slide, please. Yes. Okay, and this is, again, each sub-watershed that they broke Bessie's Creek, Brookshire Creek, and the Orchard Creek into. If you look on the left-hand side, it gives the name of the sub-watershed, and then as you go from left to right, you'll see the characteristics of that specific watershed. For example, Bessie's Creek 1, the very top line starting at the left, it's 1,594 acres or 2.49 square miles. There's a BDF value. Again, we looked at it a little bit on that in the last slide. The slope of the channel, that's how much slope the channel itself has as you come downstream. The slope of the natural ground is that number, and so on and so forth. It gives those variables in there. And off to the right, we've got some time of concentration and R values. And so all these variables have to be calculated for each sub-area. They're either accomplished by ground survey, by LiDAR, or other studies. But very detailed information has to be plugged into each sub-area so that the models can use that and calculate how much runoff, and we will get from each sub-area, and all that's combined into the main channels. Next slide, please. This is a land use map. It's really focusing on the lower portion of the watershed. We've got 90 or Interstate 10 up in the upper part there. That's just the different types of land uses. Obviously, that makes an impact. If you have a high impervious cover on a particular sub-watershed, you would expect more runoff, more volume of runoff too, than you would for an open pasture land or rice field land. Obviously, would drain a little bit different than raw pasture land. So this is just showing what the engineers were able to pick up from aerial photography and other information and incorporate that into their calculations to determine runoff. Next slide. this again goes to the BDF calculations, and if Tommy and Greg and John want to look at this some more, they can get a copy of the video. Let's go to the next slide. Okay, this slide is for the model. It says you tell the model how much water is going to be coming into it, and then this slide does the hydraulic calculations to determine how deep the water needs to get in the channel, what the channel looks like, what culverts and bridges look like. As you see along the blue lines, which are following the creek, you see these, I'm going to call them little white dash lines. And we can go back, the little white dash lines, those are cross sections. Some of those cross sections, most of them were taken off LiDAR maps, but there was also some ground survey work because there's obviously some water in the creek, and so we needed to get a good idea of what the volume or what areas beneath the water elevation, and the LiDAR can't penetrate the water, so additional work was done there. I don't know if you can see them on your computer screens, but there are also some red dots in here. Those red dots were where cross structures were being either culverts or bridges or low water crossing, some type of major structure that the water has to flow through, under, or across to continue downstream. Those were actually surveyed by field survey crews to incorporate that information into the model. Next slide. This model that was done, I'm going to try and explain this as best I can. It's what we call a 1D, 2D model. Typically what's been done in the past is a one-dimensional model. You tell the creek how much water is in it at a particular place, and you give it the area that it's got at a particular cross-section and the slope of the channel, and it calculates, okay, with those dimensions, how deep is the water going to be in this channel. So that's part of the model. But in the overbank area, where we got a lot of overland flow and water leaves the channel in some places, comes back in other places, we have overflows from Brookshire Creek and other areas. So what they basically do is they develop a grid. And by a grid, you've got these rectangular or square plates. They can range from very small plates up to very large plates, but they make up the whole area. And let's just for conversation say each plate is 50 feet. It's just a flat square plate that's 50 feet by 50 feet. And there are just tens of thousands of those that make up the whole watershed. Well, as they put the rainfall equally over the entire watershed, every 15 minutes, another tenth of an inch or half an inch or an inch of rainfall falls over the entire watershed equally. Each of these 50 by 50 plates gets that same rainfall on top of it. The computer then calculates, okay, for this plate I'm looking at right here, is the water higher or lower than all the adjacent plates? And then it determines, okay, if it's higher, which way does its water drain? Does it drain to the left, to the right, to the north, to the south? And it calculates that for every single plate, and then also determines what the water elevation is on each plate as a result of all that. And then 15 minutes later, another rainfall increment comes in, being a tenth, a half, or an inch or so, and it puts it on top of those same plates, and the model calculates for every plate again, which way does the water flow off each plate. The water can actually flow off a plate in one scenario, and then an additional inch of rain, it actually would reverse and flow back onto it. So these models are very complex and require a lot of time to run and require a lot of input, as well as a lot of review to make sure that they represent in the model what really happens on the ground in the real world. If you didn't get that, don't worry. It took me a long time to figure that out myself, and a lot of explanation. Next slide, please. Okay. This may be a little more interesting to everybody. Let me explain it to you. On the left-hand side, the wording, the location, that's giving you the location starting at the upstream end, the county line with Water County, and then it works its way downstream. The first 8 or 10 locations are in Bessie's Creek, all the way down to the river. The next 5 or 6 locations are Brookshire Creek, and then the last 4 locations are in Orchard Creek. Orchard Creek is south of 1093, also goes into Western Lakes, what they call Pecan Lake. It's referred to as Orchard Creek in this study. But if we go to the top at the county line, the very number 1, and we start working our way across, it gives a station number. That number is not super critical. You could put 10 million there if you want to, but it's the number representing a distance that the county line is from the river. In this particular case, is 98,191 feet from the Brazos River top line. Bear with me a second. That's our phone. Okay. If you move across, you'll see at that particular location, there's 58.09 square miles from Water County that drain through that particular point. It shows the flow for a 2-year event. 2 years, about 5 inches in 24 hours, and I don't know off the top of my head what it would be for 5 hours or 12 hours. But again, if you went back to that Atlas 14 chart we showed earlier, you could find that information there. But in a 2-year event, you're talking 1,566 cubic feet per second. You go over 2 spaces to the 2 deals to the 10-year event. You're looking at go one more over to the right. There you go. We're looking at 3,136 cubic feet per second. And now let's go way over to the right to the 100-year. At the county line, we're looking at 5,869 cubic feet per second coming across the county line into Fort Bend County in a 16.5-inch rain in 24 hours. And that's not a continuous rainfall. That is the peak flow rate that comes through there. And if we would go down to section 15 under the 100-year, there at the Brazos River, there you go. You can see at the Brazos River, the peak flow coming out of Bessie's Creek is almost 11,000 cubic feet per second. And it goes just a little bit to the left. There's a water elevation at the river of 90.39. And as you go upstream, you'll see those water elevations rising. Don't put a whole lot of credit on the 90.39 because that's assuming that the river is down. And so as you go upstream at each of these particular locations, like at 1093, that's 100-year rainfall is 100, almost 105 feet above sea level is how high the water gets. And to put that in perspective, if you go to the Drainage District website and look at our LIDAR map, anybody can look on there. You zoom in to a certain level, and the ground contours will show up as purple lines. It will tell you what the land elevations are at these specific areas or whatever area you want to look at. And that's based on the same data these elevations are, 1988 data. So if the water gets up to 105 here at 1093, you can look at our LIDAR map all around the 1093 area and see if it's land you're interested in or land on your property, you can tell, well, would the water be above my ground or below my ground just by comparing those numbers. One other thing I wanted to point out is if you go up to number 9, the Brookshire Creek confluence with Bessie's Creek, and go all the way over to the 100-year number. If you'll notice right there, it's 10,344 cubic feet per second, but you go up just one notch there, up to 552.99. What that's saying is the peak flow rate in Brookshire Creek is almost 5,300 cubic feet per second. I'm sorry, Bessie's Creek is 5,300 cubic feet per second. But now we're having, coming down right with that is the Brookshire Creek flow, and it kicks that number up significantly, over 5,000 cubic feet per second more. Now, you can't really see it on here, and you have to look at the model, but in reality, Brookshire Creek actually has a peak flow rate of about 7,000 cubic feet per second, but it comes through sooner than the Bessie's Creek peak flow does. And so Brookshire Creek, the peak flow has already come past this confluence point, gone down Bessie's Creek, and is either in the river or headed to the river before the peak on Bessie's Creek actually happens. And so if you just add the peak flows on top of each other, we would be looking at about 12,500 cubic feet per second. But since the peak in Brookshire Creek and Bessie's Creek don't actually happen at the exact same time, the peak flow rate is a little bit less there, and it's down to 10,000 cubic feet per second. Okay, next slide. Okay, this is a result of all the modeling. The light blue area is showing 100-year floodplain. I'm going to call it brown, light brown, or tan color, beige color, whatever that is. That's the 500-year floodplain. Of special interest and significant is the stripe, the candy stripe area. Those are what we call effective flow zones. And the significance of that is if you fill in those areas, you're not only displacing water, but you're blocking the water's ability to flow north to south or east to west in its route to the river. And so there is a lot more stipulation or requirements if you try to put any kind of fill or structure in that effective flow boundary. In general, the light blue area, 100-year floodplain area, that area is where water is typically just being stored. It's not trying to flow toward the river. It's just out there pooling and ponding, waiting its turn to get back into the main creek and make its way down to the river. So typically what we do in these blue areas, if you want to go and fill in there, you need to mitigate. So if you fill an acre of land that's got 3 feet of water over it, and you fill it up completely with dirt, you've got to provide 3 acre-feet of storage, floodplain storage, somewhere else in that general vicinity to offset that impact. The floodplain conveyance zone, though, much more significant. You can't say, I'm going to fill an acre here 3 feet and just dig an acre 3 feet. It takes much more analysis and usually much more mitigation to rectify any impacts you have there. Next slide. Okay, what this is doing is trying to, these guys take these models, and since we don't have any gauges over here, they have to have some type of ruler to try and see, are we way out in space with our numbers, or are we reasonable? And so what they're doing is they're comparing their results to some results from a 2015 FEMA study, which is if you see 2015 100-year water surface elevation, yes, right there. That's the water surface elevations that were achieved in that particular study. And if you go to the one on the left, he's pointing to now, that was a Clomer 2017. Somebody did a conditional letter of map revision, and they came up with some different numbers in there, a little bit different than the Lomer. Well, what our engineers are doing in the 2020 master drainage plan is they're comparing their elevations and their flow rates back to these other areas. And what is interesting is you'll see we've got higher flow rates than the other guys do, but we've actually got water surface elevations that are comparable to what you see in the 2015 FEMA numbers. And part of that is due to the two-dimensional modeling. It gives much more realistic values. The one-dimensional modeling is a little bit conservative when you do that, because it's assuming the water's only flowing one way. And there's some accounting for storage in the one-dimensional model, but you get a much better accounting in the two-dimensional model for the floodplain storage that occurs. Next slide, please. Okay, this is just a couple areas of interest. The county line, you can see that the floodplain, we got a high ridge separating some floodplain from the Brookshire Creek area and the Bessie Creek area. Brookshire Creek there on the right a little more, just right there. That's Brookshire Creek. Go up a little bit more. That's Brookshire Creek. Bessie's Creek is the blue line running north and south on the left, and so you can see they're not connected in any way at the county line. But as you come further down into the county, further south, the floodplain is so wide there that it almost connects the two channels together. Also, if you look down at 1093, a little bit further south, there you go. What we have there is you've got Weston Lakes, and we've got the channel called Orchard Creek. I don't have any easements at all on Orchard Creek, so there are some dams in Orchard Creek. It's an unmaintained channel, and for just this conversation, I don't have easements along the entire Bessie's Creek either. From the county line almost all the way down past the last crossing of 1489, I have no easements. From just upstream of Pool Hill Road all the way down to James Lane, I do have easements, and we do maintain that section. But what I wanted to point out is the main channel in Weston Lakes is what they call Pecan Lake, and that's where almost all their water drains to, and that is an extension of Orchard Creek. And Orchard Creek actually goes into Bessie's Creek just across the road from Weston Lakes, but it also goes into Bessie's Creek just to the east of Simonton on the left-hand side over here, about 3 inches to the left, right there, Orchard Creek. So it's confusing is how did all these channels get all twisted up and it goes in the creek one way and another way. What it is this is river bottom area, and Bessie's Creek used to be the Brazos River. And so over time, as it's migrated further to the west and to the south, it's left these other little channels that tend to intermingle with other channels and make short circuits, and some get dammed off. So it's a pretty convoluted drain system in there. But that's what we're dealing with, and all this is modeled, and the two-dimensional modeling helps account for which way the water's flowing. Is it backing up in Orchard Creek and being accounted for? Okay, next slide, please. Okay, what this is going to be is there's going to be individual sections. They broke the watershed up into individual sections, and there's going to be a cost analysis for each section, and that's what this is showing. And you can look at this on the video later on if you want to. There's not a lot of detail. We've got these same charts a little bit further down with a better description of what the costs are and what they're based on. So let's go to the next slide. I think there's about 12 or 13. Okay, there we go. Looking at this, this shows you the different sections of channel that they broke Bessie's Creek and Brookshire Creek into. As you can see, Brookshire Creek has a purple line on kind of at the very north part of the screen with a 260-foot wide right-of-way. Then it transitions to a 370-foot right-of-way as it goes down into Bessie's Creek. As you can see on Bessie's Creek, there are a number of different segments that have different widths of right-of-way that would be needed to make these improvements. And so the next several slides we're going to look at are going to give summaries of what each individual segment would cost to improve to handle 16.5 inches of rain in 24 hours. Okay, so the next slide. I missed this. This is, we asked the engineers to also look at alternatives besides just trying to dig this channel out. What about detention? What about diversion channels to the river? Let's look at other alternatives to see if there's something that's more cost effective for the entire project or even a segment of the project that would benefit us and not cost so much. And so what this is looking at is 3 potential sites where we could divert water out of Bessie's Creek and take it to the river. As you can see, they're either going right through Valley Lodge or going just north of Valley Lodge. But as we look at the results on the chart on the right-hand side of the screen there, the benefit is not very significant based on what the work would entail and what the cost would be. So we told the engineers to don't do any further investigation for that because it's just not cost effective. Next slide, please. Okay, in this chart we're fixing to look at, there's an environmental factor that has to be included in here, and there's some pipeline adjustments. And so this is kind of giving a description about some of these factors that had to be included in the construction cost, from environmental to archaeological to pipeline adjustments. And so those factors were included in these cost estimates we're fixing to see. Next slide. Okay, this is segment 1, and it gives you a description from Pecan Hill Drive to Hunt Road, and it's on Bessie's Creek. And as you can see, it's not a very long segment of channel. It's about 1,400 feet long, and I'm looking for excavation. Excavation would be about 163,000 yards of excavation. They have to haul that dirt off out of the floodplain and drop it on somebody's land. So all those costs are calculated in there. As we talked about a few minutes ago, wetland mitigation, stream bank mitigation, pipeline adjustments, all those variables are put in there, including the right-of-way cost, which at the very top line, 65.1 acres, estimated at $1.4 million. Next slide. This is segment 2, gives you a description of where it's at. Same variables on the chart, right-of-way costs, construction costs, excavation, pipeline adjustments, wetland mitigation, and this particular segment is $22 million. And unless anybody has any question about a specific segment, let's just, if you'll click each screen and it'll show you the different segment, give them about 10 seconds to look at each segment in case somebody's interested in one. If you want to stop on one, we can. But Don, if you would just kind of click through the slides, that'd be great.
This is segment 3, 19.5 million. Segment 4, 25.6 million.
Hey, Don, let me just ask one question here since he's got the cost estimates up.
Yeah.
These cost estimates, you have a lot of numbers in here, Mark, but I noticed there's a line item called stream mitigation, and it seems to be almost the highest number on each chart. What is stream mitigation?
Right, that's something that just came up several years ago. Not to change the subject, but we were working on Big Creek years ago. I got a permit on Big Creek in 1986 from the Corps to expand the channel. The county wanted to expand the channel, and they were going to plan to do other channels, and they never have done the other channels. We haven't finished Big Creek. In 2005, my permit expired. We'd run out of the ability to extend the permit, so we had to get a new permit. So we started working on that based on the old Corps requirements. Well, halfway through that thing, they came up with this new scenario called stream bottom assessment. And what that is, they grade your creek based on how it looks. They'll do a cross section at any particular point, and that cross section will apply to the next 500 feet. And it ranges from a 1 being the lowest score, not very environmentally good, to a 5 meaning, oh, we love this. It's got a lot of microorganisms in there, and the birds and the fish and the snails and the frogs and the trees, all that's great in here. They like that. So if you got a stream that has not been maintained, like we maintain our streams, we don't like trees in our streams. We just try to keep them grass lined, and that's it. So we would get a 1 on our stream. But if you go to an unmaintained stream that's got a lot of trees and vegetation there, that is going to score a 5. And they're going to multiply that 5 times the entire 500 feet. So you're going to come up with a total score there of 2,500 points. So if you're going to do some work on that stream, when you get through, that same segment of stream has to have 2,500 points or better on it. And if you say, well, look, we're the drainage district, we're going to clean this stream up, we're going to knock all the trees out and clean it up to where it's very trapezoidal and just plant grass in here, well, they're going to say, well, look, you're taking this thing from a level 5 to a level 1, so you're going to have to do something to mitigate that. And what you do is you go to a stream mitigation bank, if there is one in that specific watershed, and you buy credits in there. And there's something like $175 to $200 a foot for that credit for stream bottom assessment credits. And so that's where those numbers are coming from.
Okay, thank you.
Mark, I just transitioned over to segment 1, 100-year level service cost estimate. There we are there. I've gone through every slide.
Okay, and this is Brookshire Creek here. So Brookshire Creek has only 2 segments to it. And so with that, if somebody has questions, I'd be happy to try to answer them.